Right, welcome colleagues who are beginning to join us online, and to those colleagues who have joined us today in International House. It's a full house again in International House, and one of my great delights as director of the IAS here is that increasingly we are beginning to see larger numbers of people who are actually able to come to us in person than who are having to come and attend online. So we are beginning to have a more lively in-house and in-person event each time we meet. Welcome to those of you who are online though as well, and we're delighted that you could make it to the virtual IAS. And if you attend to the bottom of your screen, you will note that there is both a chat function and a Q&A button. Those will both be monitored during the course of this seminar today. So if you do want to ask a direct question through the Q&A function, or you want to make a comment or have a wider discursive kind of question that you would like everyone to be able to see, please feel absolutely free to use those. Those will be fed in at the end to the conversation and the dialogue after. So there's no problem about using those formats. You are very welcome to be involved and engaged and participate in the discussion. With that said, it's my great pleasure to be welcoming Vikash Vashisth today, who is an IAS residential fellow, and we waited quite a long time to be able to have Vikash here, and we are very delighted. He has come to us from India via Sweden. And again, that is a wonderful, wonderful route, and we are thrilled to be able to welcome you. And we've been really enjoying your company since the time you arrived as well. So we are delighted by this. IAS residential fellowships are fellowships that are able to be applied for direct by people outside Loughborough University to come to us for a month and enjoy networking possibilities and collaborative research possibilities with colleagues from any discipline in any area in the university. And Vikash's kind of core contact is with my colleague Gull Tasman, who is joining us today and will be doing the introduction for Vikash proper today. And they have been enjoying a whole range of communication. They were also in great communication during the period when we were hopeful of getting Vikash to be able to arrive to us. So I hope have had a wonderful time being able to be in person and work together for this period.
Thank you.
And so with that said, I'm going to turn over now, please.
Thank you. So I'd like to join Marsha to welcome you all to this session, those of you who are in the room and also elsewhere. So we have got Dr. Vikash Vashisth with us today to give the presentation, and our thanks, mine and Vikash's, are due to IAS colleagues who have allowed this journey. So Vikash joins us from Chalmers University of Technology. He started there only a couple of months ago. He is a chemical engineer, and in fact, he contacted me the first time while he was doing his PhD, because the project is quite close to some of my areas of research. So that's about high shear mixing, energy intensive processes, mixing and dispersion processes. And when we say dispersion, obviously we think of multi-phase systems. So these are cases where we aim to break up gas bubbles or droplets of immiscible liquids or break up clusters of particles. And the overall objective, the top aim, would be to generate a fine dispersion. And the size range, the distribution properties would typically be dictated by the product, the final product. So we find a lot of applications that require such processes. Some of them are for novel products. So if I quote a few, in the automotive industry, we hear more and more about batteries, automotive batteries, and they typically require a fine dispersion of particles, and that the fineness of the dispersion has got a direct relationship to the conductivity, so the performance of the battery. Again, in the automotive industry, more and more components, automotive components, are being manufactured from plastics to be able to reduce the weight of the vehicle and thereby gain from fuel consumption. And those plastic surfaces require high performance coatings, which typically would have particle dispersions and particle dispersions.
Yeah.
So when it comes to such novel products, the challenge is to make sure that we have a viable process that has worked in formulation at bench scale, but will also work for large quantities to be able to take that product to market. So those are new products, but we also have a whole range of other applications, other products. So I can quote some from bio industries as well. From the food industry, we often talk about mayonnaise to give an example of a liquid-liquid dispersion. So where we have got droplets of an immiscible liquid in another one, and the size range should be of a certain range. There are a number of applications we can find in the bio industry. So we do use energy intensive processes to be able to process fermentation broths. So where we have got an intracellular product, we have to apply high levels of energy to be able to break open the cells and get to the product of interest. So really the applications are quite wide. So to be able to apply high levels of power input or specific energy, so power per unit volume times time, we make use of certain devices. There are specific devices. They may be different from bench to large scale, but typically we would make use of batch or inline rotor-stators, ultrasonicators, and Vikash's talk relate to those two devices. There are others like stirred bead mills, valve homogenizers, microfluidic devices as well. In all of these cases, because of the high specific power input, the equipment would typically be made of stainless steel. So it's not possible to make observations of the flow field or make measurements due to the material of construction. And we do need quite detailed information of the flow field so that we can interpret the process appropriately, we can achieve success consistently in manufacturing or achieve scale up. So we often resort to numerical modeling of the flow fields. And in Vikash's work, research projects, he has done some experimental work, but also numerical modeling, and that's going to be part of his talk as well. So if I understand well, there's going to be a little bit of, you're going to cover briefly the project that you started at Chalmers University.
Yeah.
There's going to be a more detailed part relating to breakup processes using energy intensive devices.
Yeah.
He also worked at IIT Guwahati. Yes, he had a research project there, so he's going to talk a little bit about that as well to give us an overview of the very many projects that he's been involved. So on to Vikash.
Thank you. So first of all, thank you for the nice introduction, and thank you, Marsa and the IS team from bringing me here. And like I was waiting from 2008. I was in contact with Gul from 2008, and we were discussing few projects. We have developed few projects, but waited for so long to be in meet personally. But the IS gave us this opportunity to be here and discuss things and go further on maybe different projects and develop more projects with Gul. So thank you. So for today's talk, I will be discussing my research at different universities. Currently, I'm working as a postdoc at Chalmers University of Technology. And before that, I was working as a research associate at IIT Guwahati. And then before I was a PhD student at IIT Roorkee. So I will be discussing details about of my research at IIT Roorkee, but few overview of my research at Chalmers and IIT Guwahati. So for today's talk, my topic is process intensification through high shear mixing, which is basically my research at IIT Roorkee. Okay, so but before that, I will discuss my current research at Chalmers, and then at IIT Roorkee, then IIT Guwahati. Okay, so at Chalmers, I'm working on like it's a computational part of a complete computational part where I will be working on turbulent interface interaction in dispersed flows. Dispersed flows are like gas, liquid, and liquid dispersants. So there I will be like experimentally, people find that's when there is a dispersion of gas, liquid, or liquid system. So only a binary breakup is possible. People believe that, and they find it experimentally also with simulations. They have developed some numerical modeling for CFD and population balance modeling in ANSYS or other modeling softwares. But when my current research group, they did experiments and some CFD, they found that not only the binary breakup is possible, that's the possibility of binary breakage is minimum. The possibility of higher like number of like more breakage, like maybe 7, 10, 15 from single droplet is higher as compared to binary breakup. So they did some experiments and found that, and we also did some simulations and validated that theory that multiple breakage is possible. So I will be doing that research in like they have done some research on liquid dispersants. I will be doing research on both gas liquid and liquid dispersion. So like I will be using large eddy simulations or like high result CFD simulations to study the interaction of turbulence with particles. How the turbulence is affecting the particles like gas or liquid droplets, like maybe like they stretch a bit and then breaks into multiple fragments. Experimentally, it is not possible to capture all the fragments. So we may lose some like tiniest fragments, but while using simulations, we can go up to that level and capture the smallest or the tiniest fragments. So that's why we are using simulations for my current project. And we find that theoretically more than 1 metric cube of eddies of various sizes exist per cubic meter turbulent fluids. Experimentally, it is not possible to go that level. So that's why we are using simulations. And in their previous work, one of my colleagues has done some simulations and found that how the turbulent is affecting the deformation of a droplet. So he did simulations and keep everything same. For 2 different cases, he ran 2 simulations and found that the interaction of turbulence is different in both the cases. Hydrodynamic conditions were same, completely same in all the cases. But when you run 2 simulations in turbulent flows, so that you found different kind of deformation, like different deformation time, and the number of fragments are different. Like in first case, he done some simulations and found that the deformation time is 6 milliseconds. While with the same hydrodynamic condition in different simulations, he found that the deformation time is 5 milliseconds only. And the final breakup is like having 3 fragments in one simulation and in one condition, and in other condition, he found 7 fragments. So this is how the turbulence interact. Maybe in the second case, the turbulence vertices is much bigger than the previous one in this case. That's why there is the number of fragments are less as compared to the second case. Okay, and we found it like when we compare like why it is happening when we do when we keep the same hydrodynamic condition but different kind of fragments, and we compare the interfacial area with respect to time in both the cases, and found that when like interfacial area, increase in interfacial area means like the transfer of energy from vertices to the droplet and the breakage, further breakage or deformation and breakage. So like when we have 7 fragments, we found that the interfacial area or the rate of energy transfer is much higher as compared to when we have 3 fragments only. So with the same hydrodynamic condition, you can have different energy transfer from the turbulent vertices to the particles. And this is like experimentally we can't have that kind of resolution, because we can capture with 2D images, like we can record, but in the end we can maybe miss the tiniest fragments. So that then we compared our simulation data with different adaptation or mesh sizing, so that are we able to capture the smallest fragments also with our simulation, or are we still missing that smallest fragments? So we compared 2 mesh size, like when this is for the second level of refinement level, and this is for the 3rd level of refinement. And if you see, for first 5 milliseconds, there's a complete similarity between from 0 millisecond to 5 millisecond. The deformation is completely same, the stretch is completely same, but after 5 milliseconds, from 6 to 7, you can see different fragments. And when we did when we did simulation for 2nd level of refinement, we found that we are missing the 3rd. That's the tiniest fragments. So like finally we use this adaptation criteria or the 3rd level of refinement, so that we can capture the smallest fragments. Okay. This is the work they have done with the liquid dispersion. Now I will be doing this work with different kind of liquid properties, and I will be extending this work with the gas liquid system also. Okay, this is my overview about my research at Chalmers. It's a completely CFD based project. And if you have any question on this, you can ask me now, or you can ask me later after the presentation. Yeah, thank you. No questions. So I will proceed with my research at IIT Roorkee. So at IIT Roorkee, I was working on high shear mixing. I did some simulation for 2-3 years. Then I did some experiments for the applications of high shearing devices for the dispersion of particles into liquids. So basically, what is high shear mixer or rotor-stator mixers? We call it as a rotor-stator mixer also. Like in conventional mixer, we have like, this is kind of conventional mixer. We have simple impeller. It rotates at certain RPM in certain direction, clockwise and anti-clockwise. But in rotor-stator or high shear mixers, this impeller is enclosed in a stator part. Like if you can see from this impeller is enclosed in a stator part. This is the stator part. If you see, it has different openings, and they can be different. Like it is like this. Sorry, that's impeller is too big. So we don't have the smaller impeller, but generally it is enclosed in a stator part, and it rotates at very high RPM. And the gap between the rotor and stator is the main function, which generates very high shearing because of very high velocity gradients. Okay, that's how it is different from the simple impeller or stirred tank reactors. And this is the second geometry. It's again the rotor-stator, but yeah, like it's a it's a rotor. It rotates at very high RPM, and it's a teeth rotor. You can see that there are blades inside it also. Okay, like it's impaler. You can see. Okay, but it's kind of different than I use, or I just bring from the Gul today just to show you guys. Okay, it's a multi-stage rotor and the single-stage stator. Okay, because it has only one kind of stator hole, teeth. So these are different kind of geometries like people generally used. It's these are different like it's a rotor, it's a stator part. These are different stator. They have different applications practically when you use like this is what we have. It's a rotor. It's enclosed in a stator. The gap between rotor and stator is too small, very small, and that's these are different like multi-stage rotor-stator mixers. And it generally operates in two ways, either in batch or continuous. In batch, like it suck fluid from either from the bottom or from the top, and it eject the fluid from the stator holes. While in inline, it is enclosed in a jacket, and it's suck liquid from the one side and eject from the other side. And these are different stator geometries. They have different applications. Some can be used for simple mixing. Some can be used for different, like maybe a dispersion of liquid, and for the gas liquid or the solid liquid. And in rotor-stator mixer, if you can see that energy dissipation rate is very high as compared to the simple impeller, stirred or agitated vessel. While in an ultrasonication system, it is much higher than the rotor-stator mixer, but ultrasonication system is generally used for like for the small scale, not for the like large scale volume when you need a large scale volume. Okay, you can work in laboratory, but you can't use them to when you need a very high volume. These are different applications of rotor-stator mixer you can use for the dispersion, homogenization, emulsification, grinding, chemical reaction, coagulations, cell dispersants. And so that's the geometry it's very complicated. And when you do experiments in the industries, this is generally enclosed in a steel vessel, and you won't be able to see how the fluid behaves inside that mixing tank. So that's why you need simulations. That's why you need CFD work, so that you can get exact information about how the fluid is behaving inside the tank. You can have like from that simulation part, you can optimize your process also. So I did some simulations. I also developed some different kind of rotor-stator. In this, I've just changed the inclination of those stator holes, because when I'm in masters, I did some simulation on the existing rotor-stator mixer and found that the turbulence near the vicinity of rotor-stator is not sufficient for the application in solid liquid dispersion or liquid dispersion or gas liquid dispersion. That's why we changed the inclination, we changed the size of the stator holes, we increased the number of holes, we decreased the plate size, so that the turbulence or the flow is not affected by the size of the plates. So we made some changes, and we developed this one, and it has very it has a less power consumption as compared to at that time in the existing high shear mixers. So we divide this computational geometry. It's a very complicated. You can just simply see it. It's not easy to have a single like complete domain. So we divide this complete domain into different parts and analyze different criteria in different parts. Okay, so this is computational domain. It's a mesh we have used in different parts. we use total 1.3 million cells. And this is the hydrodynamics characterization we did, and we analyzed the velocity profiles for at different planes. Like we draw 3 different planes and analyze the velocity pattern, how the vectors are changing, and with respect to plane, with respect to height of the stator, also with respect to the rotor speed. And if you look at this, there is a circulation within the rotor with the stator hole. This is the stator hole. If you look at this, this is the stator hole. This is a circulation loop within the stator. And the jets seems to be very small at low RPM. You can see that's from this middle one. This is the middle plane. And if you increase the rotor speed, you found that jet size is increasing. But there is circulation is still there in the stator part. So that's mean that there can be the mixing inside the stator part also. Okay, and the jet size increase when we increase the rotor speed, but to some extent, because the flow in the bulk is too dominating, so that the size of the jets is not up to like a large distance. It decays after certain distance. And these are different flow parameters that we analyzed, and we found that mass flow rate increased with the rotor speed. And this is the energy dissipation rate that we analyzed, and we found that the maximum energy dissipation occurs in the rotor swept volume. Rotor swept volume is the volume inside that this part, the stator part. Okay, so the maximum energy, like this is the region where the maximum energy is dissipating. And if you go away from that part, you see that the energy dissipation is decreasing with the distance. Like the maximum is in rotor swept volume, then the whole region. Then there is enough energy dissipation in the jet region, while in the rest of the tank, it's very, very low. So but the area of interest is like the rotor swept volume, because if where the like dispersion is happening, that if you want to go for the breakup, that's the main reason where you will get the breakup. So in the bulk, you don't need to look, because you are more interested in near the vicinity of rotor-stator. That's in the bulk, the fluid go out from the rotor-stator vicinity. And if you look at the power number and we compare the power number with different rotor speed, power number is found to be like, it's nearly constant. It's not changing much. It's changing from 1.71 to 1.78. And that's the correlation between Reynolds number and power number. That in turbulent conditions, that's power number is nearly independent, or it's independent of the Reynolds number. But in the laminar flow, when you have the laminar flow, it's opposite. It's inversely proportional to. That's power number is inversely proportional to the Reynolds number. And we analyze different geometries. We analyze the turbulent energy dissipation rate for different geometries. This is the geometry that I have developed in my PhD. These are the 2 different geometries. They are from Silverson design. They have these 2 kinds of designs, and we found that's energy dissipation rate near the vicinity of rotor and stator is very high in this as compared to these 2 different geometries. The jets in this rotor-stator is much larger as compared to these, but the energy dissipation rate is much higher in this one as compared to this one. So when we compare the mix, we also compare some mixing characteristics for different geometries. Okay, but before that, I will discuss my like mixing characteristics in my design. So what we did like we insert a tracer here, and we analyze the mass fraction at different locations. Why because we want to be sure that there should not be any dead zone within the mixing tank. So we analyze the mixing at different locations. We use the species transform model in CFD, and then we analyze, and we found that's it took maximum time to achieve mixing in the upper part, like at the point 4 and 5. You can see that's at point 4 and 5, it took maximum time to achieve a constant mixing as compared to other part. Because in rotor-stator mixer, or in batch rotor-stator mixer, the predominant reason is the lower bulk fluid instead of upper bulk fluid when you decrease the size of the stator holes. So now I compare two different stators. Like in this, I have smaller stator holes. In this, I have the bigger stator holes. So if you compare the mixing in the whole region, you can see that with the bigger stator holes, you can achieve mixing easily throughout the domain as compared to the stator with smaller holes. So for general mixing, you can go for like a stator with the largest hole size. But for dispersion part, I did some experiments to check to compare the size of the stator. That's which one is good for the dispersion. So I did some, before that I will discuss the mixing. That's how the mixing is get affected by when we inject the tracer at different locations. So in this, I've injected tracer at different locations and compared the different geometry also at different location and different geometry. So these are three different geometries: circular holes with larger size, circular hole with smaller size, and these are the slotted one with the larger size. And we inject pressure and compare mixing, how the mixing is get affected by the geometry and also by the tracer injection point. So if you look at this, you can see that after certain time, when we have the larger holes, the mixing is easily achieved with the bigger holes, because in this also we have the bigger holes as compared to this one. So it's not easy to achieve mixing in smaller time with smaller holes. So that's why for the simple mixing, we can go for the stator with larger holes. And when if we compare the injection point where we should inject the tracer for the smaller mixing time, so we can see that when we inject the tracer at just the opening, or that's just the bottom of the rotor-stator, or just at the bottom of the tank or at the top of the tank, we can see that it's very different when we inject the tracer at different locations. Even with bigger holes, it takes much time when we inject the tracer at the top, or even at the bottom. When we inject the tracer at just at the bottom of the rotor and stator, it's easy and it took less time to achieve a uniform mixing. Like you can see, it is still not achieved throughout even half of the part of the mixing tank. While in this, it's completely maybe 80–90% is mixed. So this is the comparison of different stator in different liquids. In this, I used water and the glycerol and the CMC. It's a non-Newtonian fluid. So, and when we compare the strain rate distribution for different geometry, we can see that's a complete difference in the strain rate distribution when we have viscous fluid but Newtonian in nature, but when we have viscous fluid but non-Newtonian in nature. So we can see that strain rate distribution near the vicinity of rotor and stator is much high as compared to the Newtonian fluid. Because in non-Newtonian fluid, the viscosity decreases with the increase in the strain rate. So that's why we have like more uniform strain rate distribution near or high strain rate distribution near the vicinity of rotor-stator. This is for some simple water, which is very low in viscosity. So I did some experimental work on while comparing different geometry of rotor and stator for the dispersion of nanoparticle cluster into liquids. So for the dispersion of particles, like we initially go for the incorporation of those particles, like we incorporate powder, liquid, continuous phase, or some additives using some stirred devices. Then to break those incorporation for a finer dispersion, we use either like very high shearing devices to achieve a more uniform dispersion. So in my study, I used rotor-stator mixer and the ultrasonication system. But we can also use bulk homogenizer or just disperser to break those incorporations. And these are different breakup mechanism. When we go for the breakup of clusters through energy devices, we found we can see three different kind of breakers phenomena. One is erosion, that's second is rupture, that's third one is scattering. It's all it also depends on the energy, how much energy you are transferring from device to the particle cluster. So in erosion, like the smallest aggregates sheared off from the surface of the large agglomerates, and in shattering and rupture, you will have like the small aggregates as compared to the erosion, but they are high energy. They need high energy as compared to erosion. But when we compare like different rotor-stator mixer to analyze the breakup and to analyze the dispersion into different geometry of rotor-stator, I used silica nanoparticles, aerosol 200, and we simply mix that those particles powder into liquid with simple rod, and then we use the rotor-stator to analyze how the dispersion is going on with respect to time, or what should be the what can be the breakup phenomena that we can achieve through rotor-stator mixer while we disperse those nanoparticles. And we also compare two different geometries, like where we have bigger stator holes and where we have the smaller stator holes. So I analyzed the particle volume fraction for two different geometry. For this one, I call it a disintegrated head. I will call it as a mesh head. While we comparing, we found that initially we have a single monomodal distribution at time t is equal to 0, just when just simply mix the particles into liquids. And when we disperse through rotor-stator and analyze the particle size distribution at different time intervals, we found that the fine volume fraction increase with the increase in time. And the model has changed to bimodal. It's not a monomodal now. And if we compare based on the model, bimodal and monomodal criteria, also we can say that's the breakup phenomena. Like in erosion, we have a bimodal distribution, because we can have the smaller fines, we will have the coarser particle also, But with time, the coarser particles gets decreasing, and then the volume fraction of the fines increase with respect to time. So we found a bimodal distribution, and the dispersion, the volume fraction of fines increase with the increase in the rotor with time. And we also analyze with respect to rotor speed. So, but after certain RPM, we get that there is not much change in the dispersion. Okay, and we also used ultrasonication system for the dispersion of nanoparticles, and we analyzed the dispersion at different concentration of solid particles for over a period of 1 month. We analyze the size like periodically, like for 1 day, 2, 3, 5, 7, 8, 10, and 2 for over a period of 1 month. And then we found that the Z average of that sample is increasing after certain days when we have high volume fraction of the solid particles. But when we have like 1% of solid particles, there is no much change in the particle size. But for 10% of solid loading, we have a change after certain number of days. So but like there's not much change. It's in nano size. So the change is like from 112 to 126. It's not much change. So we can say that we achieved a like good dispersion. That can be can be stable for over a period of 1 month without adding any other additives or other solvent. We can achieve a good dispersion while using rotor-stator and ultrasonication system. And we analyzed the rheological characterization, and we found that like for different weight fraction of solid particles, there is not much change in the viscosity of the total solution. But when we increase the percentage of solid particles, that we found that there is a change in behavior from Newtonian to non-Newtonian. But that non-Newtonian behavior is again changing when we increase the dispersion time. If you look at this graph, you can see that at time t is equal to 15 minutes. There is a like little bit of non-Newtonian behavior. But if you like after 180 minutes or after 60 minutes, the behavior is again Newtonian. So initially you can have a non-Newtonian behavior, but in final dispersion you will have a Newtonian behavior even with the loading of 5 weight%. And this 5 weight% is in the glycerol solution, which has a viscosity of 100 millipascal second. And if you go for like for higher percentage of solid loading in this viscosity of continuous phase, you will get like a paste-like solution. You won't be able to disperse it. Like we also use 7% of solid loading and 10%, but it was like a complete paste. It was not easy to disperse using even rotor-stator or ultrasonication system.
Are these experimental results?
Yes, sir. Yeah.
Where do you take the samples from, get the measurements?
Yeah.
From which part of your system?
It's near to the rotor-stator part. I like it.
Sample collection point.
Yeah.
Okay. That the rheology will be different with different parts in the system.
And that's like it's for the non-Newtonian fluid. It's generally like viscosity will remain same for the Newtonian fluid.
With particles, depending on the particle concentration, the rheology.
Yeah. Yeah, could be different. Yeah. Yeah, could be different in different locations. Yeah. That's why we have analyzed the viscosity at different time also. Are we able to achieve it? Because if you can see that at time t is equal to 15 minutes, we have non-Newtonian behavior even near to the rotor-stator. But after 15 minutes, that it is because it's completely dispersed. You don't have a larger agglomerates. That's why it's changing back to the Newtonian. And these are the like SEM and TEM analysis that we have done. Like we have achieved a very small size using ultrasonication system and the rotor-stator mixer. Like initially the size, if you look at the initial size, which is very like the agglomerates are very like large in size. But when after dispersion for like 3 hours using ultrasonication and rotor-stator, you have a good like there are no bigger agglomerates in the solution. And this is power draw. We use a calorimetric test to analyze the power characteristics at different solid loading. And we found that after like if you increase the solid loading, there is no much change in the power consumption. So we can say that for higher solid loading, the system can be more efficient. And so this is what I've done in my PhD for the simulations to check the behavior of nanoparticle distribution. You can I tried to do that thing. We tried to like combine CFD and population balance modeling, but somehow I didn't do that. But so we just did the experimental work. But it can be possible to use population balance modeling and CFD to analyze the particle size distribution. So now I will discuss my research at IIT Guwahati. At IIT Guwahati, I was working as a research associate before joining Chalmers. So there, we used a multi-phase. I did some multi-phase simulations, and we used a toilet cleaner. We analyzed how the behavior, how it behaves when you just simply like you know that's Harpic. Harpic, you ever heard of? I think, yeah. So I used this Harpic. Yeah, it's very popular in India.
Any brand, it's always a Harpic.
Yeah, Harpic. So I did, and the reason behind doing this study was to minimize these finger formation, or to increase the total covered area, because if there is a finger formation on that of that liquid, then it won't be easy to clean the whole part. So the total covered area should be high instead of finger formation. So in that we use different polymer, and in their like formulations, we changed different criteria, and we found that with hydrogel, and it's a pusher, it's a locally made some polymer, we call it a pusher, and that's we found that for hydrogel and pusher we have like good total cover area in comparison to other polymers. And it's a multi-phase simulations. Like I can't like go into details because it's a they are PR, so it's not Harpic. We can't disclose many things. Okay, but we change many criteria. We change the contact angle, we change the inclination, we change the total volume, we change the different polymers, the configuration we change, and so this is what we have done. But our aim is to reduce the finger formation and increase the total cover area.
Yeah. Nice example, actually. I talk about this I used to talk about it in product formulation or product design. which is the chemical engineering module. So how chemical engineering approaches can affect the products and make them more effective.
Yeah.
So we're not involved in formulation, but some of the things that we do contribute towards product.
Yes. And simulation, it's easy, like you can have change, like without going to experiments, you can change in like inclination or contact angle, you keeping the same, then you can change their formulation based on that. So we did that. We did some experimental also about, but I was not there in person.
Yeah.
And so our group has done some experiments also.
Thank you.
Yeah.
Very much.
So thank you. This is all about my research at different universities.